Hello there, my name is Ben and welcome to this math video tutorial on quantifiers and negations. So we're going to be talking about two important quantifiers that we use in the logic of mathematics. And first quantifier we want to talk about is the universal quantifier. In the universal quantifier, we use a symbol, like an upside down A, and then this stands for all or for each. It's basically, just for everything. If you think about the universe being everything, so that's kind of where that comes from, universal quantifier. So for all or for each, this upside down A symbol. And then there's also the other type of quantifier. Kind of the opposite is the existential quantifier. And that's using the backwards uppercase E. And this means there exists. Just like the word existential, there exists. We can find something or choose something. So there is something, that we're looking for. So that's with existential quantifier. And then with the universal quantifier, in contrast to that, is considering everything for all or for each, the whole. So if we want to use, look at some statements, like there's universal statements and existential statements. Let's look at a universal statement in general form. We could say, for all, we'll say x, comma, and then we'll have a statement called p of x. P of x is a statement using the variable x. So, you could say, for all x, comma, x is greater than 3. That could be a statement, a universal statement. And then if you wanted to do the existential statement, you would say, you use the backwards uppercase E, and you would have there exists an x. And then we'd use another symbol. This is called such that. So this is what such that is. And then p of x is true. So an example of that would be, statement of that would be, there exists an x, such that x plus 2 equals 5. So that would be an existential statement. There exists an x such that x plus 2 equals 5. So we'll just make a quick note here that this symbol means such that. And that we only use the such that symbol only with the existential statement. We only use it for this type of statement. We don't really use it for the universal statement. So what we can do now is take a look at how to negate a universal and existential statement. So for the negation, we could do, we'll look at for all x, p of x. Oh, excuse me. Man, sneeze there. And if we want to look at negation, remember we either use the symbols tilde, kind of like you see in Spanish, so that means not. Or we can use this symbol like the upside down or rotated L, uppercase L shape. That's for not. So those are not. So when we find the negation, we're just finding the opposite truth value or opposite statement. So if for all x, if p of x is true, then the negation would give us the opposite truth value, meaning that that's false. So this would be logically equivalent to, and the way that we negate the universal statement is we'll negate the for all x, and we'll use the opposite existential or the opposite quantifier, which is the existential quantifier. So we'll do there exists an x, and then we have such that, and then we negate the statement, not p of x. And that would be the negation of the universal statement. There exists an x such that not p of x. And suppose we wanted to negate the existential statement, there exists an x such that p of x true, and to negate that we use the other symbol to negate. We'll say that this is logically equivalent to, we negate the existential quantifier, which is the universal quantifier, so we have all for all x, comma, and then we negate the p of x, this statement as well, so that's going to be not p of x. So that would be the negation for all x, not p of x. So that's just looking at it in general form, how it looks. We're going to go through some examples, to see how this works, in more of a concrete way, and help us to understand how to apply these ideas. So we'll get a new board here. And there we go. So let's look at an example here. So let's say we want to negate this statement. We'll say for all x greater than 0, x squared is equal to 25. For all x greater than 0, x squared equals 25. So to define the negation of this statement, we're just going to negate the universal quantifier, so that's the existential quantifier, so there exists an x greater than 0. And notice that we keep the inequality the same, so we're just saying there exists an x greater than 0, and then we have such that, because we always use that with the existential quantifier, and then we negate this statement, the p of x, which is x squared equals 25. So the opposite of that would be x squared does not equal 25. And then that would be our negation. There exists an x greater than 0 such that x squared does not equal 25. So let's look at another example. Let's say we wanted to do there exists an x such that x plus 2 is less than 7. There exists an x such that x plus 2 is less than 7. So if we wanted to negate that, let's be logically equivalent to. So the first thing we do is look at the quantifier that is existential. So we turn that to universal quantifier. So we say for all x, comma, and then we'll have x plus 2 being less than 7. This is our p of x statement. We want to negate that. And the opposite of less than is what? Greater than or equal to. So we'll say x plus 2 is greater than or equal to 7. And that would be the answer. For all x, x plus 2 is greater than or equal to 7. Okay. Let's look at one that's a little more challenging. It has another element there. Let's say you wanted to do for all, let's say we had epsilon greater than 0. There exists a delta greater than 0, and then we'll say such that f of x minus L, the absolute value, is less than epsilon. So if some of you are taking calculus, you probably learned that this is the definition of the limit, of how you would prove that a limit exists. So if you haven't, learned calculus, that's okay. That's not really important. What's important here is that we're just trying to find the negation of the statement. So the terms, the variables and everything, or the constants, don't really mean anything to us at this point. We just want to know how to find the negation. So to find the negation of this statement, we're just going to negate each of the quantifiers. That's the universal and the existential quantifiers. So that's going to be, this will be logically equivalent to there exists an epsilon greater than 0. And then we'll say such that, and the opposite of there exists is for all delta greater than 0, comma. And then we have to negate this part right here, f of x minus L. Absolute value is less than epsilon. That's our p of x statement. So to negate this, we just look at the opposite of less than, which is greater than or equal to, kind of like the last problem. So we'll just have absolute value f of x minus L is greater than or equal to epsilon. And then this would be our negation. So notice here in the last example we had more than one variable, here. We actually had we had epsilon, we had delta, and notice that we did not negate these inequalities. We kept them the same. The inequality we did negate was in our p of x statement, because we went from less than, and the opposite of that is greater than or equal to. Okay, so now we want to look at, in examples where we can find out if these statements are true or false. And the ones that are true, we can actually prove them to be true, and the ones that are false, we can disprove those statements and show why they're false. So let's say we have a statement here. Let's say we have for all x, there exists a y, and then such that x plus y equals 7. So we have for all x, there exists a y such that x plus y equals 7. So let's see if this is a true statement. And the way we can do this is we look at that universal quantifier. We say for all x, we know x can be any real number. And there exists a y. So since the y comes after x, we could actually find a y. Maybe we can find a y in terms of x such that this equation is true. So remember, so what we can do is say let x be a real number. And then since there exists a y, that means we can choose a y. Choose y equal to something that'll make this equation true, x plus y equals 7. And the way we do that is we go do some scratch work to the side. We'll say x plus y equals 7. There's our equation. And then if we solve for y, just subtracting x to both sides, we see y equals 7 minus x. So there we go. We found what our y is in terms of x. So choose y to be 7 minus x. And then we do find out what x plus y is. So we have x plus y equals x plus, and we know y, we can substitute that with 7 minus x equals x plus 7 minus x, and we see the x's are going to cancel, so that just gives us 7. And that actually is the proof to the statement y is true. And usually you can include a symbol at the end of your proof. Sometimes I use a diamond colored in to indicate I am done. There are other symbols that people use, like or the initials QED, which is Latin. Quid erat demonstratum, which means which was to be proven. You can use that, QED. There's also other different symbols. Some people may want to put like a smiley face, right? Something like that, saying they're happy that they had actually proved the statement. So you could put anything you would like at the end just to indicate that the proof is done. Or even some people put a simple just bar, colored in bar. So one of my favorites is the diamond or QED. So there you go. So that statement was actually true, so we could prove it. But let's look at another example here where the statement may or may not be true. And let's take a look at that kind of problem. So let's say we have there exists an x greater than 0, and we have such that for any y greater than 0, we'll have x times y is equal to 4. So we're going to look at this statement. There exists an x greater than 0 such that for any y greater than 0, we know that x times y is 4. Well, since x and y are both positive numbers, we know if we multiply two positive numbers, we get a positive number. And we know possibilities of multiplying two positive numbers to get 4. We know if we did some scratch work to the side, we get 1 times 4 is 4. And and 2 times 2 is 4. So, those are main possibilities there. But we're thinking we could choose an x maybe, but y has not been introduced yet. Notice that x is first. There exists an x greater than 0. Notice that the order of the quantifiers have changed. There exists comes first, and the universal quantifier comes second. So we may run into some issues here with proving this statement. So the question is if you're not sure if it's true, how can you show that it's false? How can you show the statement's false? And the way that you can do that is what we learned earlier. We can do the negation, find the negation of this statement, and prove that that's true. So if we define negation of this statement and prove that it's true, we show the original statement's false. And that's what our aim is here. So if we negate this, we have there exists an x greater than 0. That means we could use for all x greater than 0, comma. Then we can say there exists a y greater than 0 such that xy does not equal 4. Because the opposite of xy equals 4 is xy does not equal 4. And so now the quantifiers have changed order. So notice that for all x can be any real number greater than 0. Y, we need to choose a y, some y in terms of x is greater than 0 such that x times y is not equal to 4. So we can begin by just letting x be greater than 0, right? Because that's the universal quantifier. It can be any number greater than 0. And then there exists a y greater than 0. That means we can choose a y. And so we need to do some scratch work here over on the side. So we need to figure out, a number y in terms of x is positive that would not give us 4 if we multiply by x. So we could choose, let's see, if x times y, what if we wanted something that was not 4, say some other number? We could do, say, 1. We could choose any other number size 4, and then if we solve for y, we get y equals 1 over x, divided by x to both sides. So there we go. We found our value for y, and then we can put that into our proof. So y equals 1 over x. Then this is where the magic happens, right? Then we do our multiplication. So we have then x times y is equal to x times whatever y is, 1 over x. And notice that x's are going to cancel and you get 1, but that's not equal to 4. So therefore we can include that. So we can say, so original statement is false. Because we found an example, right? We found a y such that if we multiply it by x, we get something other than 4. In this case, we got 1. We could have let y be 2 over x. Maybe 3 over x, or 7 over x, 10 over x. Any of these would work because the if we multiply x and y together, we would not get 4. And that's what we were after. So there's an example where the original statement is false, and so you would take negation of that statement, which we got right here. Here was the negation. We proved that that was true, and that's why our original statement was false. Okay, so this is Ben, and thank you for watching this video on universal, existential quantifiers and negations, and even learn how to prove and disprove some statements with quantifiers. Please stay tuned for future math videos here on the Math channel, and you have a good day. Take care. Bye-bye.